Okay, so this is the Scientech 2802 kit. Over here you have this, it has broadly three modulation techniques in one kit: pulse code modulator, differential pulse code modulator or DPCM, and continuous variable slope delta modulator. So we are going to firstly see the pulse code modulator. This is going from left to right. This is an external input which you can give through this input, right? It can be some external signal or any analog signal, or you also have various options of internal signal. For example, here you have the various analog signals like sine wave, square wave, triangular wave, and two arbitrary random signals. Over here you can change the frequency also from 500 hertz to 1 kilohertz, like that, right? Note that you don't have a knob to continuously change the frequencies. You can just select between some fixed frequencies of the message signal which you want to modulate using this digital technique PCM. So over here you have the modulation technique selection. Right now it is selected as per the lights. It is selected as pulse code modulator. You can select differential pulse code modulator or the continuous variable slope delta modulator. Right? So we'll keep it to pulse code modulator over here. In the pulse code modulator, the first stage, as you can see, is the sample and hold. So we give the input signal, let's say it is square wave with some 1.5 kilohertz frequency, to the sample and hold block. The sample and hold block essentially is given the sampling frequency or clock from this input, wherein it takes the samples at the defined frequency. How to change this frequency is over here at the bottom. If you can see, the sampling frequency can be chosen between four values: 4 kilohertz, 8, 16 or 32, and corresponding the line speed is the sampling frequency multiplied with 8, that is 32, 64, 128 and 256. So this can be changed, which would change the clock of the sample and hold circuit, essentially how frequently the samples need to be taken, right? Then that signal is passed to the analog to digital converter, right? And analog to digital converter would change our this square wave, which has been sampled, to the corresponding digital value. So let's say it is 5 volts, so it would be 101. If it is 1 volt, it would be 001. So correspondingly it would be, so over here it is 8 bit, so it would be 2 raised power 8, that is 256 values of 256 different levels can be selected over here using this ADC, analog to digital converter. That is fed to the parallel to serial port, because we would be sending our data serially through the channel, right? So that parallel data over here, 8 bits, need to be converted into serial 8 bits, which would be sent over the channel bit by bit. And this is our channel, it would be fed to the channel. We'll come to the channel section next, but we'll firstly see the waveforms. Okay, as you can see that that above waveform, the yellow one is the input signal, which is our message analog signal in this case, which is a sine wave of 500 hertz. We are feeding that to the sample and hold circuit, and at the output of the sample and hold circuit, you have this particular sampled analog same waveform, where the sampling frequency has been taken to 4 kilohertz. So it is almost 8 samples per period. You can firstly let us see whether it is this, we can change the frequency of the signal, right? So it can be either 500 hertz or 1 kilohertz or 1.5 kilohertz, and like that. You can also notice that as I increase the frequency, the sampled signal at the bottom changes its shape. That's because of the Nyquist criteria, that the sampling frequency should be at least more than twice the signal frequency, which you can clearly see, right? So right now the signal is 3 kilohertz, and now back to 500 hertz. for it, this example. You can change the nature of the wave. Can be sine, square, or triangular wave, right? Or any arbitrary input like this random two sinusoids added. Let us take for this example sine wave again back. So this is the output of the sample and hold, the bottom one. Now we'll see the output of the analog to digital converter. This is our output of the ADC, and which is given to the parallel to square parallel to serial converter, and this is our pulse code modulated signal. As you can see that as I said, right now the sample frequency is still 4 kilohertz, and you can see that there are 8 samples in one period because the signal frequency is 500 hertz, and this is the digital data, ones and zeros. In ones and zeros would be transmitted by this PCM. Now interesting thing to note is the comparison between the frequency or the clock which is given to this parallel to serial converter. If I show it, this is this one, right? This is the clock signal, the rate at which the parallel to serial converter in this case is working, and if we compare it with the sample frequency, which I'll change the yellow one to, you can clearly see that the parallel to serial converter is 8 times faster than the sample and hold sampling period, that is sampling frequency. That is because if we reduce the times per amplitude, it will be more clear. Yes, as you can see, 8 times faster parallel to serial conversion than the sampling of the signal. That is essentially, this is the clocks only. This is because your serial converter, your serial data would be 8 times faster than the parallel data, because we are sending the bits now one by one, ones and zeros, instead of sending the sampled values parallelly, right? So this is the conversion. Now what we can do is change the sampling frequency from 4 kilohertz to 8 kilohertz, double, right? So it is now doubled, right? Over here you can see the serial the clock with the parallel to serial converter also increases, the frequency also increases 8 times, and you can increase the sampling period. This is 16 kilohertz, and correspondingly changes. Okay, now this pulse code modulated signal shall be passed through the channel, and you have the various options. You can either have the signal which is to be transmitted, pulse code modulated signal. Either you can attenuate it, right? There are two values of attenuation, 7.7 decibels and 12 decibels, right? Note that 7 decibel is lesser than 12 decibels, which is better because it is the ratio of the input to the output. Or that attenuated signal would be passed through an amplifier, and you can see the amplifier output as well. You can change the amplifier values also to 2 values depending on the attenuation. If the attenuation is high, you will amplify it higher. If attenuation is low, you need to amplify it lower. Once you do that, there is another option. Instead of this passing it through this attenuated channel, you can pass it through a low pass filter. Now we know that every channel is allows only certain frequencies to pass through it, and this is actually emulated over here using a low pass filter, and with some cutoff frequency, let's say 5 kilohertz in this case. Any signal greater than that would not be allowed through the channel, and any realistic channel has a finite this frequency bandwidth which it allows to pass. So we can check that as well by changing the channel to a low pass filter. So instead of an attenuated channel, you use a low pass filtered channel to see the frequency response. And or you have the option to simply pass the signal transmitted through a noisy channel, and here you have the various noise levels, 3 levels. You can select between level 1 means the largest noise added to your signal over here, right? This is this input signal added to it noise, level 1, level 2 or level 3. Level 3 is the lowest amount of noise which we'll see from the waveforms, and you can correspondingly give the output depending on if your signal is attenuated. It would be amplified through this amplifier, which is a gain stage simply. If it is passed by a low pass filter, then you can pass it through this stage over here, which is clock and data recovery, right? Over here it automatically gets activated, right, which would essentially recover the data, especially at high frequency elements, can be recovered through this recovery stage. Why it is clock recovery? Because at the receiver we have to demodulate the same modulated signal, and we have to know the sampling frequency in order to demodulate it correctly, and that sometimes can be calculated through the received signal. The clock can be calculated through the received signal. That is what this stage does. And finally we'll see all the waveforms, right, of the different channels and their effects. So the above waveform is the transmitted pulse code modulated signal, and the below yellow waveform is the attenuated one. You can either attenuate it, right now it is I think 7.7 decibels, or you can attenuate it and it would be 12 decibels. So after attenuation you can see the reduction in the received signal, but thanks to the amplifier you can amplify the signals. As you can see now, this is the amplified signal, and you can amplify it to 2 levels, right? Either high amplification or low amplification. So over here you can see that it has been further amplified. Now another characteristic of the channel which you can see is the low pass filter. So if we look again, right, this in blue above waveform is the transmitted signal, and when it is passed through a low pass filter, so this is the transmitted signal and low pass filtered output. Now the channel is acting as a low pass filter, which will not allow higher frequencies to pass. Right now the sampling frequency I have set to 16 kilohertz. What I can do is I can increase the data rate or the line speed correspondingly. I can firstly, let us see the basic 4 kilohertz, right? One thing to mention is that these values are continuously changing, because if you remember, the message which we transmitted was a sinusoidal waveform, and the sinusoid changes continuously. So these values actually are changing, ones and zeros. These values it is encoding, right? So now I increase the sampling frequency. You can see the edges have started shifting, right? This is because now these higher frequencies are not allowed to pass by the channel. If I further increase the sampling frequency to 16, right, you can see again the curve is getting changed, right? If I stop it, you can see that the higher frequencies, as from the Fourier knowledge, is that the higher frequencies are missing now in these received signal, right? If I further go on increasing the sampling period, sampling frequency to 32 kilohertz of the transmitted signal, now you can see over here, for example, this the lot of higher frequencies are getting removed, right? Maybe in 10 to 20 kilohertz and above, right? So this is the effect of the low pass filter. Now what we are going to do is we will see the effect of channel noise. Note that we are separately seeing all these effects. Now I'll see the effect of the noise. This is the effect of the noise. As you can see, we amplify it. Sorry, let me change the scope. So as you can see that this is noise at the highest level, at level 1. You can see that this noise signal got added to your transmitted signal, and if you have various levels of noise, this is the least one, right? This is the least noise added. And if this noise signal we want to see, we can also check the noise signal which got added in our channel. So this is the noise which got added to a channel, and you can increase the noise levels accordingly. Your received signal would be distorted. Now this noise or the higher frequencies which were missing in the low pass of the channel due to low pass filter of the channel, or they can be removed very efficiently using the clock and data recovery and the low pass filter stages of the pulse code demodulator, which we will see next. Okay, in the receiver section, this was our pulse code modulated wave, which is passed through the appropriate channel model. Either you attenuate the signal, and on the receiver the signal is amplified. This amplification can also, by the way, happen in the midst of the channel at appropriate, which we call as repeaters. For example, your under the ocean optical fibers have regular repeaters after 20 kilometers, right? If you use the low pass filter model of the channel, then of course the higher frequencies, for example, because obviously over here the bits are in ones and zeros, which are square, perfectly square wave, so they need to be, the higher frequencies need to be again added to the signal, because unless that is not done, if that is not done, the pulse code demodulator will not be able to differentiate between a 1 and a 0, digital 1 and a 0. So that is done using this clock and data recovery. This stage not only can retrieve the clock, that means at what frequency the pulse code modulator had sampled the signal, but also most importantly, for example, for a low pass filtered output of the channel of the signal, it can, those high frequencies are again added to the received signal, and then you can pass it through the pulse code demodulator. And note that if noise is added, then it has no role in that case, right? Noise, which is the inappropriate levels, they can be removed by this low pass filter stage. This pulse code demodulator essentially does this bit stream ones and zeros, it converts into 8-bit again parallel data output, and that 8-bit data is fed to a digital to analog converter, and finally we'll see this signal would be exactly as this sampled signal, of course, right? Now the higher frequency elements again will be added removed through this low pass filter, and the output over here would be the same message analog signal which we transmitted over here. This we'll see from the waveforms. Okay, now in order to see the functioning of the clock and data recovery stage, above is the output of the channel, which is acting as a low pass filter, right? And the higher frequencies, as you can see, it has been exaggerated, so the higher frequencies are missing. The sampling frequency I have taken is 32 kilohertz, capped to the maximum. We see the higher frequencies being removed at the received signal, but they need to be again restored. So we pass this signal through the clock and recovery stage, which again restores the high frequency elements. You can see perfect ones and zeros square wave appearing over here, and this recovered signal, PCM signal, would now be passed through the pulse code demodulator. The demodulator would first do the serial to parallel conversion, so that we'll see the serial to parallel conversion, and finally it will do the digital to analog conversion. So these would again, serial 8 bits would become again parallel 8 bits, and then the digital to analog converter will give the appropriate values of those 8 bits, starting from 0 to 256 levels, right? The output of the demodulator, pulse code demodulator, is this, right over here. Because the sampling frequency is very high, we need to reduce the scope so that we can see the changes. So here you are, this is the transmitted signal at very high sampling. That's why it is looking, you know, continuous. And this is our PCM signal. If we you know, change the sampling frequency, reduce the sampling frequency to, let's say, 4, right? And you can see right here, you can see that the sampling periods are clearly visible over here, which are almost 8. So in order to remove this from the pulse code demodulated output, you can pass the signal through the low pass filter, so that these higher frequencies would get removed and you get a smooth wave just as the transmitted signal. So if we pass it through the low pass filter, this is the output of the low pass filter. So the higher frequencies have been smoothed out, right? Now, because again the the sampling frequency is very less in this case, of 4 kilohertz of the sinusoid. If we increase the sampling frequency to almost, let's say, double, 8 kilohertz, you can see this is just the signal as we had transmitted. I will show the transmitted signal over here. This is the signal which we have transmitted, and as you can see that it has been cleanly demodulated and low pass filtered output, right? Now what we'll do is we will see the changes in signal frequency, and the output of the low pass filter would be you know, seen over here. So right now the signal frequency is 500 hertz, right? If we increase it to, let's say, 1 kilohertz, you can see the instability over here, because now the message signal is getting, you know, its frequency is getting increased. So low pass filter, which is at the output last stage of the demodulator, will not be able to will remove the important frequencies, right? If you again increase the signal frequency to 1.5 kilohertz, you can see the effect. Now 2 kilohertz, and finally if it is 3 kilohertz, the input, you know, signal frequency, the low pass filter can not you know, detect the signal, right? Because it's a second order Butterworth filter with a cutoff frequency of the 3 decibel cutoff frequency of almost 5 kilohertz,